Good evening, welcome back students, welcome to Yupp Master, the school foundation program. I am your chemistry teacher Dr. Sripad Rao. So, in the last class we have gone through the topics what we are going to cover under the class 9th under this particular program, that is foundation program. Okay. So, in the last class I have also given you the information about the class the topics what we are going to cover under class 8th, and we have discussed some questions based on the topics that are going to be covered under the class 8th under this particular Yupp Master program. Okay. And you can also follow the 8th class classes as well if you are interested, and also advise your friends as well as well-wishers to download the Yupp Master app and get in connect with the online classes. Okay. So, it is a free now, you can access through the Yupp Master app, download the Yupp Master app. So, you can have the facilities, the online classes you can enjoy, as well as you can use this app anywhere, anytime through any device, and you can also get the clarification of the doubts 24/7. So, we the teachers are available online 24/7 to clarify your doubts. So, whatever doubt you are going to get, you just post the doubts through the app question and answer application there. And in this particular foundation program, we are also going to discuss some of the previous question papers related to the Olympiad as well as the higher competitive examinations. Okay. So, today what we are going to discuss is with respect to the gaseous state. We have discussed under the last class that the first topic that we are going to cover under foundation program in 9th class is gaseous state, right. So, in case of gaseous state, before we go into the detail or the advanced discussion of the gaseous state, let today I want to give you a brief discussion or brief introduction to the gaseous state, and then we move to the higher levels like main as well as advanced level, and once we finish sufficient amount of theory concepts, then we look into the objective type of question that are going to be appeared in the are going to appear in the examinations, or those are already appeared in the competitive examinations. Okay. Right. Let us move on to the concept like matter. What is matter exactly? So, according to chemistry, we can define the matter anything, okay, it can be anything which has a mass. So, it has going to have mass and it is going to occupy some volume. So, anything which is going to possess some mass and which is going to occupy some space or some volume is said to be matter. Book, for example, if you take, it is a matter, it has some mass. So, it weighs something, right, and it is going to occupy some space when you keep it on the table. So, it is going to occupy some volume. So, it is going to have mass as well as volume. This pencil, for example, marker, it has a weight and it is going to occupy some space if I keep on a table. Okay. And the chemical substance also going to have some mass and it is going to occupy some space. Air is also a best example of matter. It is going to have some mass. If you, for example, if you fill a balloon with air, the balloon will weigh some weight. Okay. So, it is going to possess some mass and it is going to occupy the volume of the balloon. So, it is considered as a matter. Okay. So, matter is anything which has mass and which is going to occupy space, which is going to occupy some volume, is taken as matter according to chemistry, right. So, when you look at the classification of matter. So, matter generally classified in based on the physical state, the components can be classified as solids, okay, liquids and gases. So, general we take the different classification, physical classification are the based on the states of matter is solid state, liquid state, gaseous state. So, of course, we can take the plasma, Bose-Einstein, condensate, all can be taken as a classification, but generally we focus on these three particular classification components. Okay. We are going to discuss in chemistry, we are going to discuss the solid state. Of course, the solid state requires some fundamental development of chemical concepts. So, the solids concept can be discussed little later when compared with the other two. and of course liquids we are going to discuss under some concepts under the solutions, and of course some concepts which we are going to discuss after the gaseous state. And gaseous state is the first learned concept of matter which we are going to learn, and of course easy to understand, easy to grasp the concept. Once we finish the gaseous state, at the end of the gaseous state we are going to come across the liquids and their properties, and after the learning of gas and liquids we focus on the solid, little advance after this particular two topics. Okay, right. How can we differentiate solid, liquid and gas? How to differentiate? I think you have seen solid, sugar is a solid, right. Liquid, the best example for liquid is water. You have seen water, liquid. Gas, air is a mixture of gases. Oxygen is a gas, nitrogen is a gas, hydrogen is a gas. So gas is one more part. So you can observe the examples of solid, liquid, gas in our day to day life. Solid materials like a table, a chair, a cot, a bed, all are solids. Liquids, water, okay, alcohol, the sanitizers what we are using now, the main solvent for that compound liquid is alcohol. Okay. Gases, the air is the best example, gas. For our existence we require oxygen, oxygen is a gas. So the total amount or the area of the sun is made up of hydrogen gas. So we can see the gases at different places. Okay. So in day to day life we come across different examples of these liquids, gases and solids. So where we are going to have a difference? For example, in the case of a solid, the components or the atoms or the molecules are held together very tightly. So the packing, if you observe, the packing of molecules or atoms in case of solids is very close, and they are very close enough with one another, they are sitting side by side and thereby they get rigidity. Okay. So in the case of a liquid, if you observe, the distance between the atoms or the molecules of the components are more and they are little separated. But when you observe the gases the distance is still large enough that the gases molecules can move independent of one another. So when you look at the arrangement of atoms, in case of solids the atoms are closely packed, whereas in the case of liquids there is a separation that can be clearly seen between the particles or the atoms or the molecules, and in the case of gases the atoms and molecules are separated by large distances. So the distance increases a lot. And one more thing that we can observe is, if you observe these atoms, the atoms are very closely packed. Since they are closely packed, the force of attractions are more enough in this particular. So they have high force of attraction acting in this particular molecules in the case of solids. But in the case of liquid, the force of attractions are intermediate between that of the solid as well as gases. In case of gases, the attraction forces or the separation between the gaseous molecules is very large. So the forces of attraction or repulsions is very less in this case. Of course, liquid will have a force of attraction in between that of the gases as well as solids. Okay. And when you observe, solids will definitely possess a volume as well as a shape. Okay. But in the case of liquids possess a definite volume, but the shape of the liquid is cannot be predicted. They does not have a definite shape. Generally the liquid will acquire the shape of the container in which we are going to store. For example, if I am storing water in a tumbler, it will take the shape of the tumbler. If I take the water in a pot, of course the water is going to take the shape of pot. Okay. So similarly, if we are going to use different shaped vessels, thereby the shape of that particular liquid can be seen. So liquids will have a definite volume, but the shape is not, they does not have a definite shape. But whereas solids will have a definite shape as well as definite volume. So shape is present, definite shape as well as definite volume is present in the case of solids, whereas liquids they will have a definite volume. So definite shape is not possible. In the case of gases, definite volume, they neither have the definite shape, definite volume. So here the gases generally acquire, or that they are going to take the shape of the container in which the gas is stored. For example, if I am taking small size balloon, so the gas is going to occupy the volume available in the small sized balloon. If I take a big sized balloon, so automatically the gas is going to occupy the big size of the balloon. So it does not have any shape and it does not have any volume. So it is going to occupy the shape, the volume that is provided for the gas. So, the gases, liquids and solids can be easily, their properties can be easily understood with respect to the arrangement of the constituent particles and how the forces are acting on them and how they are going to be separated. Since here in the case of solids, the gas, the particle or the molecules or atoms are arranged very closely with one another. So, these are incompressible, further compression is not possible in the case of solids. Whereas liquids, of course, if you observe, when you compare with the gases, the distance between the atoms and the molecules in the case of gases is very large. So, they can be compressed easily. So, highly compressible components are gases. Of course, we cannot compress the liquids and solids. In the case of liquids also, the compression is very small, because the distance between the atoms and the molecules in the liquids is very small. Okay. Of course, here there is no gap, they are closely packed. So, liquids and solids are incompressible, whereas gases are highly compressible. Okay. So, how this way we can easily identify the different properties of the matter in terms of solids, liquids and as well as gases. Okay. Right. Let us move or let us focus on the gaseous state. Okay. So, in case of gaseous state, the gaseous state is the simplest state of all these 3 states of the matter. It is the simplest state we can consider among the 3 different states of matter, just now what we have discussed. So, among the 3 states of the matter, gases is the simplest state. Okay. So, it can be easily understood at the earlier stage. Then we can generally focus on the properties of liquids as well as solids, right. So, here gaseous state generally characterized by some of the properties, physical properties that we can generally observe in the case of gases. Okay. So, what are the properties? Let us discuss those properties of gases which can be characterized the gaseous state. Okay. First one, if you observe, they are highly compressible. Gases are highly compressible. For example, if you are taking oxygen in a balloon, okay. So, if I enclosing the oxygen in a balloon, so the balloon size we can slowly decrease up to certain limit. Okay. So, thereby we can say that the gas can be highly compressible, and moreover, as I told you, the separation between the atoms of gases or the molecules of gases are very large. So, since the distance is very large, so we can make them to come closer by compressing, by applying the pressure we can make them compress. So, the gases are highly compressible. First and foremost property of gases is they are highly compressible components of matter. Okay. If we observe the second one, gases will exert pressure equally in all possible direction. Let us say I have taken a balloon filled with a gas, let us say oxygen. So, oxygen will exert the same kind of pressure in all the directions, whether it is taken towards the bottom side of the balloon or the right side of the balloon or the left side of the balloon or the top side of the balloon, the pressure exerted by the oxygen gas will remain constant. So, it is going to equally exert the pressure in all possible directions when it is stored in a container. If I am taking a square container, a container of square shape, let us say, so I have a gas inside it, so it is going to exhibit the pressure equally in all 4 directions. Okay. So, it is going to show the pressure in all the directions. So, gases will exert pressure equally in all the possible directions. So, whatever may be the direction that is possible, whether it is toward the corners or toward the left or toward the right side, upside or the downside, whatever may be the side you are going to take, the gas will exhibit or it will exert the same kind of pressure. So, gases exert pressure equally in all the directions, in all possible directions. Okay. Right. If you observe the next property, you can clearly see that gases have much lower density than solids and liquids. So, here the density, we know density can be calculated, density equal to mass by volume, mass by volume. So, it is a ratio of mass and volume, ratio of mass and volume is density. Okay. So, when you look at the density of the gases is very low. It is saying that the gases will exert or they will show lower density when compared to the solids and liquids. What is the reason? As I told you, the separation between the gaseous molecules, So, separation if we observe, so I am writing again those molecules or atoms of the gases where the separation is very large. Since the separation is very large, they are going to occupy this much volume. So, the volume because of the large separation that is present between the molecules of the gas or atoms of the gases, okay, they are going to occupy large volume. They will occupy large volume. Since they are occupying the large volume, so volume size is increasing, the volume size is increasing, but in case of density formula if we observe, where is the volume? Volume is present in denominator, not in the numerator. Since it is present in the denominator, as the volume size increasing, as the volume is increasing, what happened to the density? Density will decrease, simple, they are inversely proportional to one another. If one is increasing, other will decrease. So, if I am going to take equal masses of solid and liquid, okay, equal mass of solid and liquid as well as gas if I take, okay, the mass occupied, the volume occupied by the solid is very small when compared with the liquid, and of course, the volume occupied by the liquid will be small when compared with the gas, because here in the case of solids the atoms of the molecules are closely packed. So, they are the volume, for example, if I am arranging these atoms in a case of a solid, so they are going to occupy only this much volume, not more than that. And in the case of liquid if I observe, so in the case of liquid the separation is intermediate between the atoms. In the case of liquid with respect to the solids and gases, it is going to occupy this much volume, okay. So, when you take the volume, this is the volume of a gas and this is the volume of a solid and this is the volume of a liquid. So, if you observe clearly, the volume occupied by the solid is very small. So, when the volume is small, density will be more. And of course, when volume of the gas, if you observe, volume of the gas is larger and automatically therefore the density is going to decrease when we are taking equal masses of solid, liquid and gas. For example, I have taken 1 kg of solid, 1 kg of liquid, 1 kg of gas. Let us say 1 kg of what do you call the wood piece, okay, 1 kg of water liquid and 1 kg of oxygen. So, if you observe, of course, the volume occupied by the wood piece will be less when compared to the volume of the water, and of course, when you take 1 kg of oxygen gas, it is going to occupy a huge volume. So, the volume of a gas will be very large and because of the high volume, density will be lower. So, gases will have much lower density when compared with liquid and solids. So, when you compare to the solids and liquid, the density of gases is very low, right. So, when you observe this one, gases do not have fixed volume and shape. So, the shape and volume is not fixed for the gas, okay. For example, if I am filling a gas into a small balloon, I am filling the same gas, oxygen gas, into a larger balloon. So, when you fill the oxygen gas into the small balloon and the same amount if I am filling in the large balloon, the gas in small balloon, it will occupy the small total volume of the balloon, and here also the oxygen gas will occupy the total volume of the large balloon. So, when you look at the oxygen, it does not have any fixed volume, okay, since it is occupying the volume of a small balloon and the same amount will also occupy the volume of the larger balloon. So, volume is not fixed in the case of gases. So, gases do not have fixed volume. What is the shape? For example, if I take the volume, the first shape, the shape of this one and the shape of this one are different. So, the two balloons will have a different shapes, and if I am taking a particle or the vessel which has a shape of a cube. So, if I am filling the oxygen into this one, it is going to occupy the volume of cube. If I am taking a cone, okay, so the gas is going to occupy the shape of the cone. So, here the gas which I have taken, like for example, in this case oxygen gas does not have a fixed volume because it can occupy the small balloon, or the same amount can also occupy the large balloon. So, the shape is not, the volume is not fixed in this case. And if we observe it is going to have, it is going to take the shape of the container in which it is going to be stored. For example, if you are filling in a balloon, it is going to take the spherical shape. If you are taking in a cubical vessel, it is going to take the cubical shape. If it is filled in a conical flask or it is a conical shaped container, it is going to occupy the conical shape. So, the shape is not fixed, volume is not fixed. Therefore, we say that gases do not have fixed volume and a fixed shape. The shape is not fixed as well as the volume is also not fixed. But what happens? It will acquire the shape of the container and volume of the container. So, if I am making the oxygen gas to enter into the balloon, it will occupy the volume of the balloon, it will take the shape of the balloon. Okay. If I am taking the same oxygen gas into this cube vessel, it is going to occupy the volume of this particular vessel and it is going to take the shape of that vessel. And if I am taking this oxygen gas into the conical shaped vessel, it is going to take the shape conical shape and the oxygen gas is going to occupy the total volume available for it within this particular conical container. So, it is going to acquire the shape and volume of the container, and gases do not have a fixed volume and fixed shape. The shape is not fixed, the volume is not fixed, and it is going to occupy the shape of the container, it is going to acquire the shape of volume of the container in which the gas is going to be stored. So, it depends upon the container shape and container volume, right. Next is gases mix evenly and completely in all proportions without any mechanical aid. For example, if I am going to take a balloon, okay, so I am taking a oxygen gas and I am taking a nitrogen gas. Generally the gases are filled or they are kept in a what do you call the cylinders. Okay. So, I have taken oxygen cylinder and I have taken a nitrogen cylinder. I am making some oxygen amount go into this one balloon and I am making the nitrogen to go into the same balloon. So, I am making oxygen and nitrogen to enter into the same balloon. Now, this balloon has oxygen gas and nitrogen gas. Okay. So, a mechanical aid is not required in this case to mix them evenly. So, as soon as the gases enter the container, they mix completely and evenly without any mechanical aid and they will mix in all proportions. So, we cannot separate, it is not possible for us to separate them because of their equal proportions, completely mixing in all proportions. So, this is the great property of the gases which we come across, that is gases will mix evenly and they will mix completely in all proportions, in all directions they will go and occupy and they will mix up with one another without any mechanical aid. So, generally in the case of some of the liquids, when you take a liquid and mix with other liquid, they will not generally mix with one another, but when you stir them automatically they start mixing with one another. For example, when you take a solid and in a liquid, they will not mix sugar in water, when you start stirring automatically sugar starts dissolving. So, without any mechanical aid, the gases will mix up with one another in an even fashion and they will completely mix in all proportions. It is not with 1:2, 1:3, they will mix up with a complete proportion in all proportions and they mix in even fashion, not in odd fashion. That is to say that they are, if you take one portion of a balloon, you are going to get the same components of oxygen, nitrogen when you take the other part of the balloon. So, the mixing is even, it is not an odd one. Okay. The mixing will be even and the mixing will be complete in all proportions for the gases. So, a mechanical aid is not required, no need to shake them, no need to bother about them, just make the gases to enter into that container and close it. They will automatically go because of the diffusion process or effusion process, which we come across in further discussion of the gaseous state. Okay. So, this can be seen. For example, if some person who has used the perfume, when he enters into a room, automatically the smell will spread throughout the room. What does it indicate? So, mixing of these gases takes place. So, the perfume is a gas, it is mixing with the air is a gas. So, mixing will be even and complete and it will take place in all directions and thereby the person who is sitting other corner of the room can also get the same smell of the perfume. Okay? Right. So, these are the 5 different properties generally we come across in case of gases. Okay? Let us look at some measurable properties. So, as far as the gaseous state is concerned, we are going to bother much about the measurable properties of gases. Okay. So, before we enter into the measurable properties of the gases, let me give you the number of elements which are present in the periodic table which are gases. Do you know how many elements in the periodic table are gases? So, we know that all elements are classified or arranged in the long form of the periodic table or the modern form of the periodic table. So, when you observe the modern form of the periodic table, so in that hydrogen gas, the helium gas, okay, in the first period of the periodic table, and then we have oxygen gas, nitrogen gas and fluorine gas along with neon gas from the second period of the periodic table, chlorine gas, argon gas from the third period of the periodic table, krypton gas, xenon gas and radon gas. So, these are all noble gases, and hydrogen, nitrogen, oxygen, fluorine, chlorine are the other gases which are present. Of course, oxygen, nitrogen, fluorine, chlorine are non-metals, they are covalent molecules, hydrogen is also covalent molecule. So, these are the noble gases which are existing as monoatomic and remaining are existing as diatomic molecules. So, if you count, of course, these are the elements which are going to be appeared in the nature in the form of gases. So, if you take around 11 elements in the periodic table are gases. Okay. So, total 11 elements in the periodic table are gases: hydrogen, oxygen, nitrogen, fluorine, chlorine, helium, neon, argon, krypton, xenon and radon. So, the noble gases plus hydrogen, oxygen, nitrogen, fluorine, chlorine are existing in nature as gases. Okay. So, 11 elements in the periodic table are appearing in the nature as gases, right. Coming to the measurable properties, what are the properties that we can measure? So, measurable properties of the gases, generally we measure the mass of a gas, we can measure the mass of a gas. Okay. So, the mass can be taken as a measurable property of a gas. And the second one, if you observe, pressure can be considered as a measurable property of a gas. We can consider or we can take pressure as a measurable property of a gas. And of course, volume, the volume in which it is going to be taken is also a measurable property of a gas. We can measure the volume of a gas, and also we can measure the temperature of a gas. So, temperature of a gas can also be measured. Okay. So, we are going to measure the temperature of the gas. Okay. So, these are the general pressure, volume, temperature, mass and weight of the gases can be measured. So, the measurable properties are very important in identifying the behavior of the gases, and these are all very important in calculation part. The numerical part that we are going to come across in gaseous state, we are going to focus on these measurable properties. How we are going to correlate the one measurable property with the other measurable properties. Of course, scientists have worked on the measurable properties and their correlations, and then they have formulated the correlations or their experimental results in the form of laws. So, these laws are generally called as gas laws. We can of course Boyle, Robert Boyle, Charles law, Gay-Lussac, Avogadro, all these people have worked extensively on gases, and their experimental results were formulated in the form of a law, and we are going to learn them in the form of the gas laws. Okay. Of course, once we finish all the introduction part to this gaseous state, we will focus on the gas laws, etc. Okay. Right. So, here if you observe, the state of a gas is generally described by the relationships of variables such as mass, volume, temperature, pressure. So, mass, volume, temperature, pressure are taken as measurable properties. So, the measurable properties are mass, volume, temperature and pressure. Okay. Right. So, let us focus on these measurable properties and how we are going to calculate the masses, volume, pressure and temperature of the gases. What are the units that we are going to use in case of gases, and how we are going to convert one unit into the other unit for the measurable property. Okay. Right. In case of the gas, let us look at the mass. Okay, the mass of a gas can be determined experimentally by weighing the container in which the gas is taken and then take the weight of the empty container, then subtract the empty container weight from the weight of the container with the gases. For example, let me take a container. I have a container with me, so I have a gas inside it. So I am taking the weight of this container along with the gas. Let us say W1 is the weight of the container with gas. Okay, I am taking the weight of the container along with the gas. Let it be the weight of that container along with the gas is W1 grams. Okay. Now I have taken the gas out, so I evacuated the container. So the container now does not have any gas inside, and now I am going to weigh this particular container, empty container, evacuated container. The container, a gas is removed, now it is evacuated and no gas is present in the container. Now I am taking the weight of this container. Let us say the weight of the container, empty container obtained is W2 grams. Now we generally, when you subtract these two from one another, weight of the gas can be obtained. So weight of the gas will be taken as the weight of the container along with the gas minus weight of the empty container or evacuated container. So W1 minus W2 will give us the weight of the gas that is taken. So first empty container weight has to be considered and the container weight along with the gas has to be taken, and subtract the empty container weight from the weight of the container along with the gas, and thereby you are going to get the weight of the gas. So weight of a gas can be easily obtained by subtracting the weight of the empty container from the weight of the container having a gas. Okay. So this can be done easily through the balancing material that we are going to use. Okay. So the difference of the two weights will give us the mass of or the weight of the gas or the mass of the gas. Okay. The amount of gas can be generally in terms of chemistry. Whenever we look into the chemistry, the weight of a substance, whether it is a gas or it is a liquid or it is a solid, we generally take in terms of moles. So we are going to look into the weight of the or mass of the gas in terms of moles. How we are going to calculate? So the moles can be calculated by using the formula moles generally represented with a small n. We are going to use small n in order to indicate the number of moles. So number of moles is equal to weight of the gas. Okay, we are going to take the weight of the gas divided by gram molecular weight of the gas if it is a molecule, or it is going to take gram atomic weight of the gas if it is an atom. Okay. So weight divided by gram molecular weight will give us number of moles. So generally, for example, let me take we are taking oxygen gas. So I am taking an oxygen gas, around 16 grams of oxygen gas I am using. Okay, I am using 16 grams of oxygen gas. How many number of moles are present? In that case, number of moles small n equal to weight of the oxygen. Weight of the oxygen is 16. Molecular weight of the oxygen, 2 oxygen atoms are combined to get O2 molecule. So 1 oxygen atom atomic weight is 16. So 2 oxygen, 16 into 2, 32. So 16 here divided by gram molecular mass of oxygen is 32. So 1s are 2s are 1 divided by 2, so it is 0.5. So 0.5 moles of oxygen gas is going to be obtained from 16 grams. So in order to determine the mass of a gas, we can also use the moles of a gas. So in almost all chemical reactions, whether it is a solid involving or a liquid involving or a gas involving, we always look for the number of moles. Mole is weight by gram molecular weight in the case of molecules. If it is an atom, in that case weight by gram atomic weight. Since we are using gas, so I am writing directly as weight of the gas divided by the gram molecular weight of the gas or gram atomic weight of the gas if we are taking noble gases. Okay. So weight of a gas we generally determined with respect to the number of moles. If we particularly want to know the weight of the gas, in that case we are going to take the weight of the container having the gas, and then we take the empty weight of the empty container weight, and then subtract the weight of the empty container from the weight of the container having gas, and thereby we get the weight of the gas present in it. Okay, right. So, here the number of moles we are going to calculate in terms of mass in grams divided by molar mass. So, the moles can be calculated by mass by gram molecular mass or gram molecular weight. So, mass is a measurable property of a gas. So, depending upon the weight that we are going to take, the mass is going to change, right. Next is the volume. So, volume is also measurable property of a gas. Now, if you observe the gases as we have previously discussed, they do not have definite volume. So, they do not have a definite volume. So, therefore, the gas is going to occupy or acquire the volume of the container in which we are going to store. Okay. So, as a gas fills the whole vessel when it is put in, the volume of the gas is equal to the volume of the container. So, in case gas is taken in a container, what is the volume of a gas? Do not bother, no need to worry, just take the volume of the container. Okay. So, if the volume of the container is taken, so that is taken directly as the volume of the gas, because the gas will distribute evenly and completely in all proportions in all the directions of the container in which it is going to be taken. If you are going to take a small balloon, it is going to occupy the total volume. If it is going to take a larger balloon, it is going to occupy the total volume of the larger balloon, or if you are going to take a cubical container, it is going to occupy the cubical container volume, etc. So, volume of a gas is nothing but the volume of the container, simple. Okay. So, we are going to consider only the volume of the container as the volume of gas. Okay. So, in this case, how we are going to measure the volume? Okay. So, generally when you look at the units of volume, so SI units, you know, it is a meter cube. SI unit of volume is meter cube. So, other generally commonly what we are going to encounter is decimeter cube, centimeter cube, and even we are going to use the liter and milliliters as the units for volume. The SI unit, students, please make a note, SI unit is meter cube for volume. Okay. But we are going to generally, whenever we discuss the volume of water or volume of a liquid or a volume of a gas, we determine in terms of liter, 2 liters, 1 liter, 100 ml, milliliters. So, we are going to discuss in terms of milliliters or in liters or in centimeter cube or decimeter cubes, but the SI unit of volume is meter cube. So, whenever we are going to calculate the numericals with respect to the SI units, in that case you have to substitute the volume in terms of meter cube. So, meter cube is the SI unit of gas, centimeter cube, decimeter cube, milliliters, liter. These are the general terms what we use for our convenience, okay, because in order to get the convenience we are using the liters and milliliters. It is easy to handle, okay, but exactly the speaking SI unit will be meter cube. So, what could be the relation between these components? How we can correlate meter, millimeter, decimeter, centimeter, etc. We know that 1 meter will be equal to how many centimeters? 100 centimeters. So, if I write 100, I can write it as 10 to the power of 2. Can I write 100 as 10 to the power of 2? Yes. So, I can write 10 to the power of 2 centimeter. But what is the unit SI unit of volume? Meter cube. So, cubing on both sides. So, if I take 1 meter cube equal to 10 to the power of 2 centimeter cube. So, I am cubing on either both sides of the equation. Okay. So, when I cube 1 meter cube, 1 to the power 3 will be 1 meter to the power cube, power 3 is meter cube. So, 1 meter cube equal to 10 to the power of 2, again power 3. So, it will be 10 to the power of 6, 2 into 3, 10 to the power of 6 centimeter to the power 3 centimeter cube. So, 1 meter cube will be equal to 10 to the power of 6 centimeter cubes. 1 meter cube will be equal to 10 to the power of 6 centimeter cubes, because 1 meter equal to 100 centimeters, 1 meter equal to, I am writing 100 as 10 to the power of 2 centimeter. So, cubing either side of the equation, 1 meter whole to the power 3, 10 to the power of 2 centimeter to the power 3. So, 1 to the power 3 is 1, meter to the power 3 is meter cube, 10 to the power of 2 to the power 3. Okay, 10 to the power of 2 power 3, so it will be 2 3 is 6, so 10 to the power of 6 centimeter cube, centimeter to the power 3 centimeter cube. So 1 meter cube equal to 10 to the power of 6 centimeter cube. So this is one correlation that we can derive between the meter and centimeters. Similarly, if we are going to take 1 meter equal to 10 decimeters, deci means 10 to the power of minus 1, 10 to the power of minus 1 and 10 to the power of 1 gets cancelled, you get 1 meter. Okay. Centi means 10 to the power of minus 2 meters. So 100 centimeters, 10 to the power of minus 2, 10 to the power of plus 2 gets cancelled, we get 1. So 1 meter equal to 10 to the power of 1 decimeter. Okay. Now if I am taking cubing on both sides, cubing on both side of the equation, so what we are going to get? So 1 meter cube will be 1 centimeter to the power 3 equal to 10 to the power of 1 into power 3 is 10 to the power of 3 decimeter power 3. So this is how we can correlate, or we can correct the decimeters when given in terms of meters, and we can convert meter into decimeter. So 1 meter cube equal to 10 to the power of 3 decimeters cube. 1 meter cube will be equal to 10 to the power of 3 decimeter cube. So if you observe overall, 1 meter cube is equal to 10 to the power of 3 decimeter cube, 10 to the power of 6 centimeter cube, 10 to the power of 3 decimeter cube and 10 to the power of 6 centimeter cube. Okay. So this can be observed from the calculation part. And similarly, we can take 1 ml equal to 1 centimeter cube. So 1 milliliter will be equal to 1 centimeter cube. 1 milliliter equal to 1 centimeter cube. So similarly, we can take 1 liter equal to 1000 centimeter cubes, or we can take 1000 milliliters. 1 liter is nothing but 1000 milliliters. Milli means 10 to the power of minus 3. So 10 to the power of minus 3 and 10 to the power of 3 will get cancelled out. So we get 1 liter. So 1 liter equal to 1000 ml. 1 ml is equal to 1 centimeter cube. So whenever we say 1 centimeter cube, it is nothing but 1 ml only. So 1000 ml means 1000 centimeter cube. 1000 ml means 1000 centimeter cube. So 1 liter equal to 1000 ml, 1 liter equal to 1000 centimeter cubes, and 1 centimeter cube equal to 1 ml. So this also easy converting unit that we are going to use, liters to centimeter cubes. Okay. And if you observe, 1 liter will be equal to 10 to the power of 3 centimeter cubes. So I can write 1000 as 10 to the power of 3 centimeter cube, or I can write it as 10 to the power of 3 milliliters. I can take it as 10 to the power of 3 milliliters or 10 to the power of 3 centimeter cube. And since if you correlate these two, 10 to the power of 3 decimeter cube equal to 10 to the power of 6 centimeters cube. Okay. So if I divide both sides with 10 to the power of 3, I will get 1 decimeter cube equal to 10 to the power of 3 centimeter cube. So I can write it as 1 decimeter cube. So in other words, we can say that 1 decimeter cube is nothing but 1 liter. 1 decimeter cube is nothing but 1 liter. 10 to the power of 3 centimeter cube will be equal to 1 liter. So 10 to the power of 3 ml will be equal to 1 liter. 1 liter means 1000 ml, milliliters, or 1000 centimeter cube. That is to say that 1 liter equal to 10 to the power of 3 centimeter cube. 1 liter equal to 10 to the power of 3 ml. If I want to express the liters in terms of decimeters, so 1 decimeter cube is equal to 1 liter. 1 decimeter cube equal to 1 liter. How we are getting that one? Just now we have derived 1 meter cube equal to 10 to the power of 3 decimeter cubes, 10 to the power of 6 centimeter cube. So when you divide this one with the 10 to the power of 3 and 10 to the power of 3, this becomes 1 decimeter cube equal to 10 to the power of 3 centimeters cube. So The conversions are very easy. So, we can convert one unit into the other units in the case of gases. So, this can be done easily. So, please students try to write down these things in a notebook. Always keep a pen and paper with you. Try to note down the points what we are going to discuss. Make a note of it. And based on these concepts, we are going to have some numerical part on this discussion. Okay. So, students, today let us stop at this volume measurable property of a gas. Tomorrow we are going to discuss about the pressure as well as the temperature, and some more concepts we are going to discuss in